Hi everyone, welcome to Lecture 25 Part 2 on Degrees of Belief, Reasoning Under Uncertainty. The objectives for this video are the following. So after watching, everyone should be able to, number 1, explain how we reason under uncertainty. Number 2, calculate subjective degrees of belief from preferences using the second representation theorem. And number 3, describe the Ellsberg paradox and why it's problematic for subjective utility theory. Okay, so last time we were talking about reasoning under risk, and expected utility theory is the mathematics of reasoning under risk. We saw the first representation theorem, which under certain conditions said that you prefer one lottery P to another Q if and only if your expected utility of P was greater than or equal to your expected utility of Q. This time we'll be talking about reasoning under uncertainty, so recall the difference between uncertainty and risk. A situation involving risk is one where the probabilities are objective, like betting on the colour of a card drawn from a randomly shuffled deck. Everyone agrees on those probabilities. A situation involving uncertainty is where these probabilities are subjective, like betting on a horse race, where you don't know which horse will win, but your degree of belief in one horse winning might not be the same as someone else's degree of belief in that horse winning. Now, when we modelled situations of risk, we spoke in terms of preferences over objective lotteries. The probabilities involved in the lotteries were objective. But when we model situations of uncertainty, we can't speak in terms of preferences over objective lotteries because we no longer know the probabilities involved. They are subjective now. So, in order to model situations of uncertainty, we need a different setup. And to do that, we're going to think about acts. So, what's an act? Well, first, we define a state of the world. So, consider a horse race between two horses, Arthur and Tommy. What are the possible outcomes of this horse race? Well, there are two, given in the table here. A stands for Arthur and T for Tommy. So, this sort of thing is what we mean by a state of the world. It's an exclusive and exhaustive list of all the possible outcomes in a certain scenario. And we then say that an act is an action that's defined by the outcomes it gives in each state of the world. So here are some examples. Act F, a $10 even money bet that Arthur will win. And Act G, a $10 bet at odds of 2 to 1 that Tommy will win. Now the payoffs according to these acts are shown in the table. And by even money bet, I mean that if you bet $10 that Arthur will win, and if Arthur wins, you get $20 back. So you get your stake back plus your stake again, so a net gain of $10. And by a bet of 2 to 1 odds on Tommy, I mean you bet $10 that Tommy will win, and if Tommy does win, you get your stake back plus 2 times your original stake, so a net gain of $20. Using that, you can verify that this table is accurate, but we're not going to dwell on the table here. Now, instead of preferring one lottery to another, we can talk instead in terms of preferring one act to another. And we model these situations using our ideas from expected utility theory again. Because we're reasoning under uncertainty rather than risk, we call this subjective utility theory. The mathematics, though, is the same as what we said last time, right up until we stated the first representation theorem, which, if we remember, said this. Let x be a finite set of prizes, and curly greater than or equals to be a binary relation on the set of lotteries on x. Then curly greater than or equals to satisfies the V&M conditions, if and only if there exists a function u from x to the real numbers r, such that for any lotteries on x, we prefer P to Q if and only if the expected utility of lottery P is greater than or equal to the expected utility of lottery Q. Now though, we're not talking about lotteries anymore, we're talking about acts, and there is a corresponding representation theorem which we'll call the second representation theorem. And that says this. Let x be a finite set of prizes and omega be a finite set of states of the world. So think about the horse race from before. Let curly greater than or equals to be a binary relation on the set of acts on omega. Then curly greater than or equals to satisfies conditions S if and only if there exists a function u from x to the real numbers r and a probability function p from omega to the interval 0, 1, such that the probabilities in omega all add up to 1, and this is the conclusion, we prefer act F to act G if and only if the subjective expected utility of act F is greater than or equal to the subjective expected utility of act G. So there's a lot going on again, and here S is a list of conditions that your preferences have to satisfy, like VNM was last time. S stands for savage, to whom these conditions are usually credited, and just like last time, we won't be concerned with the conditions themselves in this course. You won't have to know them for assignments or tests, and we'll assume they hold in all the examples that we look at. Instead, it's the conclusion of this theorem that we're most interested in. So like before, we're not going to prove this, we're interested instead in applying it. So to make sense of everything on the screen, we're going to talk through an example. In the example, we will again show how to recover subjective degrees of beliefs from one's preferences about acts. So to make things simpler, I'm going to give you the utility function in this example. So let's return to our bets on the race between Tommy and Arthur. Now, since winning $20 is the best thing that can happen to me in this situation, let's say U of 20 equals 1, and since losing $10 is the worst thing that can happen to me, let's say U of minus 10 is 0, and if I make the bet, exactly one of these outcomes is going to happen to me. Let's suppose further that I'd be reasonably happy with winning $10 so that U of 10 is 0.7. And now we think about the acts, so consider acts F and G from before. Act F said a $10 even money bet that Arthur will win, and Act G is a $10 bet at odds of 2 to 1 that Tommy will win. Now let's suppose we are indifferent between acts F and G. And the degrees of belief we're interested in is the degree of belief in AT, that is the degree of belief that Arthur wins, and the degree of belief in TA, so that is the degree of belief that Tommy wins. Now, I want you to pause and have a look at the payoffs according to each act. Think about what the expected utility according to Act F is, and when you've done that, move the video on, because there'll be a question. Well, the expected utility according to Act F is degree of belief in AT times U of 10, plus degree of belief in TA times U of minus 10. Since U of minus 10 is 0 and U of 10 is 0.7, this is just 0.7 times degree of belief in AT, so degree of belief that Arthur wins. Now pause again and think about what the expected utility according to Act G is, and when you've done that, move the video on because there'll be another question. The expected utility according to Act G is the degree of belief in AT times U of minus 10 plus degree of belief in TA times U of 20. And again, when we substitute the values in, we've got U of minus 10 is 0 and U of 20 equals 1, so this simplifies to just degree of belief in TA. Now, since we're indifferent between acts F and G, by the second representation theorem, the expected utility according to Act F is equal to the expected utility according to Act G. So, using what we've just shown, that means 0.7 times degree of belief in AT equals degree of belief in TA. Let's call this equation star. We also know that these degrees of belief must add up to 1. That is, degree of belief in AT equals 1 minus degree of belief in TA. Substituting this into equation star, we see that 0.7 times 1 minus degree of belief in TA equals degree of belief in TA. When we expand those brackets, we get 0.7 minus 0.7 times degree of belief in TA equals degree of belief in TA. And rearranging, 0.7 equals 1.7 times degree of belief in TA. Finally, when we divide each side by 1.7, we obtain that the degree of belief in TA, so that Tommy wins, is 0.41. And this is my subjective degree of belief in Tommy winning the race. And so we know that my subjective degree of belief in Arthur winning is 1 minus 0.41, which is 0.59. So again, what have we done? We've recovered our subjective degrees of belief from our preferences over acts and our subjective utilities. This time we reasoned under uncertainty rather than risk, and there'll be plenty of practice in the assignments with recovering degrees of belief and subjective utilities from preferences, both over lotteries when we reason under risk and over acts when we reason under uncertainty. So the most important thing to be able to do is follow this example. So what we've seen over the course of this video and the last is that expected utility theory is our working model of reasoning under risk, and subjective utility theory is our working model of reasoning under uncertainty. There are many situations in which these are good models to use when we're thinking about how to decide between acts or lotteries, or predicting how people will choose between acts and lotteries. However, the models aren't perfect, and we're going to end this video by exploring one example that shows subjective utility theory has some problems when it comes to describing behaviour, and this is demonstrated by the Ellsberg paradox. So the Ellsberg paradox says this: consider a bag that contains 99 balls, coloured red, black and green. We know that there are exactly 33 red balls, but the exact number of the other colours isn't known. And a ball is drawn randomly from this bag. You have to choose a colour. So consider this. If the ball is of the colour you choose, you win $1. And the question is, what colour would you choose in this situation? So pause and have a go at it. Now consider this outcome. If the ball is not of the colour you choose, you win $1. The question again is, what colour would you pick? So pause and have a go at it. Now, when different subjects are asked these questions, an overwhelming majority of them choose red in both questions. That is to say, in the first situation, an overwhelming majority of the subjects bet on the event that the ball is red, and in the second situation, an overwhelming majority bet that the ball is not red. So let's examine what's problematic about this. If your degrees of belief in colours red, black and green are PR, PB and PG respectively, then having a strict preference for the act of betting on red in the first situation means P of R is bigger than P of B and P of R is bigger than P of G. But having a strict preference for betting on red in the second question, which most people do, means that 1 minus P of R is bigger than 1 minus P of B, and 1 minus P of R is bigger than 1 minus P of G. And if we rearrange those equivalently, that's the same as saying P of R is less than P of B, and P of R is less than P of G. And this clearly contradicts the consequence of preferring to bet on red in the first question. So this is a problem for subjective expected utility theory, because it contradicts the basic assumption that the individuals involved have well-defined preferences over acts, from which we can then go and calculate a well-defined degree of belief. The paradox shows that we might have preferences from which we recover contradictory degrees of belief. Now this has led to much literature trying to analyse what's gone wrong here. That's beyond the scope of this course, so we're going to leave this issue here by concluding that decision-making processes and the theories we use to model them are not a straightforward affair all of the time. So that brings us to the end of our excursion through expected utility theory and subjective utility theory. Next time we'll look at the second way of talking about probability that we introduced at the beginning of Lecture 25, Part 1. That is, we'll talk about probability in terms of relative frequency. So have a go at your self-reflection questions, and I'll see you all next time.